Do
One guy whose sole job is to do that.
they probably have an AI to do it, just detect keywords like hacking and security or terrorism,
And they pay a human to just see if it's worth looking into or not.
and then they'll send me the bill.
Find his internet history.
Tag, we just wasted $20 million on checking whether you're okay or not, so you're gonna pay that.
Could you at least been something of a terror? He said sometime.
Okay.
I always thought it was so funny how people get so get insecure about full body scans at the airport, and then they proceed to get on the airplane, open up their Facebook account, and post all their personal information on the internet.
Yeah, I got it twice, so I was just lucky. Yeah, a complete pat down. I'm not talking about just, scanning.
Oh man, that sucks.
Yep.
Man,
They make you take your shoes off.
Hmm?
They make you take your shoes
Oh,
off.
you have to take your shoes off now. Yeah, unless you're younger or if you have a special. If you travel a lot,
I don't travel no more.
okay. If you travel a lot, they can give you a special tag on your ticket to basically say that you have pre-checked or pre-flight or something like that. Yeah, pre-check. So those people get through the lines faster. They don't have to take off their shoes and stuff like that. Because I'm guessing that they thought, hey, if you have traveled so many times already, we can trust you.
What if you just earn their trust and you just break it?
Exactly. And they're thinking, people who are planning to do bad things, are kind of more, usually are more rushing to do it, and they wouldn't plan out things like that. Of course, that's an incorrect assumption for the most part. Okay, so I'm going to run this program. So when I run it, it's asking me for a password. Okay, so I'll type in the password. Uh, okay, and it will say, nope, this is not the correct password. So that's the acronym of, not acronym, this is the abbreviation because you cannot pronounce that as a word. So this is an abbreviation of Read the Fine Digital Millennium Copyright Act. Okay, you can choose alternative words for the F. Your choice. But I'm using FINE. I'm using FINE, fine. Okay, Read the Fine Digital Millennium Copyright Act, which basically says any attempt to circumvent copyright or copy protection mechanism is illegal. It doesn't matter what you do with it, okay? You can be doing it because, oh, I like Sony so much that I want to spend my own time to help them debug their own software so that other people cannot circumvent, the Sony copyright protection. Even if you have that mindset and you disclose only what you find with Sony, it would still be illegal in the United States, okay? So that's the part of what the Digital Millennium Copyright Act is doing, is to make all of that stuff illegal. Which also opens up an interesting question. If you bought a DVD, okay, like fully legit, you bought it from the store, okay, and you go like, well, what if I scratch the DVD? I want to back up the content of the DVD onto another DVD. It's not even on a hard drive, it's not on Google Drive, you just want to make a backup copy and you bought the movie. Now remember, when you buy a movie on a DVD, what are you actually buying?
the right to the movie.
Exactly, you're buying the right to play that movie according to some constraints. You cannot do it, like in a neighborhood, block party. Okay, that's actually not part of the agreement. It is only for personal, private viewing. Okay, so you play by all the rules, and the law does allow you to make a copy. That is actually part of the law that says that you can make a copy if you own the right, if you purchase the right. Except the DVD itself is encrypted. So the act of making a copy involves, guess what? Decrypting the DVD, which is an act to circumvent copy protection mechanism. So that itself is illegal. But after you make a copy, it is actually perfectly legal to own that copy as long as you actually purchase the copyright to begin with. Do you guys see the problem in this?
Yes. The result is not legal.
Exactly, which means you cannot get the result because the process is not legal. And I think the people found out how to decrypt DVDs on the very first day that they came out with DVDs. I think using a Perl script too. a very short Perl script. So that was kind of interesting. All right, so I can try to run this program, using a dictionary attack or something like that, but that's going to be very difficult. So what I'm going to do is to try to see if this program will crash if I give it a password that is too long. In other words, I'm trying to put myself, me being a hacker this time, I'm trying to put myself into the shoes of a careless programmer who's going to say, well, people are going to type in the password, right? How long is it going to be? I don't think anyone's going to enter a password that is more than a kilobyte long. Okay, so they make that assumption, and then they allocate as a local variable only 1,024 bytes, in a subroutine to temporarily store the password. So I'm guessing like, well, if that is the case, I might get a chance to kind of crack the program. If that's not the chance, maybe I cannot crack the program. So what I'll do is I'm going to give it a very long password. Okay, so I will first do this with a not so smart approach. Okay, so the not so smart approach is to repeat a pattern. Okay, just like that. There are 16 characters in this case. So I'm just going to repeat this pattern many times. Okay. Okay. Just repeat it many times. I can't even. So we have 1,500 and something bytes now. I'm gonna save it, and this time when I run the program, I'll redirect it from this particular file. Now I understand that not all programs would accept the password through standard in. I know that's kind of a dumb assumption, but there are ways to kind of trick a program into thinking that you're typing a lot of stuff. Okay, even with a dialog box, even with a fully GUI program that has a dialog box, you can actually have your own script to type as if it was you in a dialog box as a super long password. Okay, so you can look up those programs. I mean, they're fairly common. So this approach is actually valid even if it is a fully GUI program. So I go like this. Oh, the program crashed. That's a good sign. It is a good sign because it means the programmer, whoever wrote this program, was not careful. Because otherwise, it should continue to give me this is, the wrong password, or it would even tell me your password is too long, it is invalid, or something along that line, or just come back silently and without letting me through the program. But the fact that it crashed, a segmentation fault is a crash, meant the program was not designed to handle such a large input. Cool. I might get a chance to crack this program after all. So the next question is, okay, so how is it crashing? So I need to figure out how this thing is crashing. GDB is my best friend, okay? So instead of that's all right. So I'm going to run this program inside GDB. Now remember, this program, I have already, the source code of this program is long lost, okay? I can't even remember what the source code was, okay? And because I only use it like once per semester, I cannot really remember the program that well anyway. There's no debug information left in this program, and that's why I use stripped as the extension, meaning that it has no debug information left in the executable. There's no way for me to reverse back to which line. It's just the executable here. So when I run this program and it crashes, it just gives me the location of the instruction that is causing the segmentation fault. Okay. So at this point, I need to basically start with this and look for as many clues as I possibly can in order to quote unquote crack the program. So the one thing that I can always get access to are all the registers. So I look at all these registers and go like, okay, we're looking for something that looks really suspicious. Which part of this screen looks kind of suspicious to you? The error flag, E flags? The E flags are basically the usual flags that we deal with, like the 0 flag, carry flag, sign flag, and that sort of stuff. That's not very suspicious. REX. RCX. RCX it's not too bad. Which one looks like a sequence of characters, just in reverse? ASCII codes. RBP, okay, that you're correct. So RBP looks like, reversed ASCII code. 30 is the ASCII code of 0, 31 is the ASCII code of 1, and so on. It's spelled backwards, okay, because it is a little endian processor, which means the least significant byte is the one that has the lowest address, and that's why it looks kind of backwards. Well, that looks like a part of our input file. So that means whatever content we put into that file has an influence on how the program crashes. Is that okay? Okay, so this is good. Another register that is really helpful when I'm trying to crack the program is RIP, RIP. RIP stands for instruction pointer. It is equivalent to our PC, our own program counter. In other words, it's telling us which instruction is directly causing the segmentation fault. Okay, the attempt to execute which instruction is crashing the program. So that may be helpful to me too, because knowing which instruction is stepping on something that is not supposed to step on may tell me how I can change whatever is stepping on so that it would actually do something that I want it to do. Okay. All right, so now we can look into some commands in GDB. X stands for examine, and then the slash separates the command itself from the format where you want to display content in memory. Okay, so I specifies instruction. In other words, I'm disassembling whatever is at the location that I'm going to specify here. Okay, the location I'm going to specify is where the program counter is. But we don't have PC, we have RIP instead. So IP once again stands for instruction pointer, which is the same thing as our program counter. Okay, so it shows me that it is a return instruction. Now remember, the return instruction does not exist in the toy processor because I intentionally want you guys to kind of examine how to do it. But this is basically the three instructions kind of combined into one single instruction. It will copy whatever the stack pointer points to into a temporary register, and then copy that temporary register into the program counter, and between those steps I also want to increment the stack pointer. Okay, so if we're crashing because of the attempt to execute this instruction, what should I look at next? This is the return instruction. What should I be looking at next? On the stack, right? The key is, where is it pointing to on the stack? So we can look at the stack pointer, okay, which is RSP, and the stack pointer only tells me the location. The location is not the problem. It is what is at the location that is potentially the problem, right? In other words, this is the stack pointer, and the return instruction is choking on whatever the stack pointer is pointing at because it is an invalid return address. That's why it's choking. So I want to find out what return address it is attempting to return to. Okay. So once again, we can use the X command, and this time we'll display 8 things. Okay. Each one is a byte, and it is in hexadecimal. And this time I'm going to use RSP to specify where I'm dumping these locations from, because I want to see, oh, you're trying to treat these 8 bytes as a return address. Which 8 bytes are we talking about? Enter. Okay. Ooh, that looks really suspicious, doesn't it? Because we are looking at the ASCII code of 8, the ASCII code of 9, lowercase a, b, c, d, e, f. Oh, isn't that stuff the kind of stuff that I have in the file when I specify that password that's way too long? Cool. But this is the part where, that also shows that I was kind of dumb to use a repeating pattern, because I can't tell which pattern, which part of the file is responsible for these 8 bytes. Because it's a repeating pattern, it could be any place that I have 8, 9, A, B, C, D, E, F. And there are many repetitions like that. It's going to take me a while to figure out which one we are talking about here. Well, we can do 2 things. So what we can do here, okay, let me get out of GDB first. So we know that whatever file I was using as a test password, We are looking at the A, B, C, D, E, F that is causing the potential issue here. And we have a lot of repetitions like that. So one thing we can do is to change this file so that each one of those patterns is unique. So I can change the F into uppercase A and then B, C, D, E, F, and so on. So that's one way to do it. Okay, so we'll go ahead and do it that way. So replace this with A. Okay, I'm looking at all the F's with uppercase B, C, D, E, whoops, F, whoops, nope, uppercase F, G, H, I, J, K, L, M, N, O, P, oops, Q, R, S, T, U, V, oops, W, X, Y, Z, and then we can start to use maybe punctuations. Okay, so we can use exclamation point, @ sign, pound sign. Oops, where is it? Okay, this is supposed to be the pound sign, the dollar sign, the percent sign, caret, ampersand, asterisk, and then the last one is open paren. I'm just going through the top row of the keyboard. Okay, so save it, go back into GDB. Oops, I forgot to specify the executable. So GDB hack1, run the new password file. It's going to crash again, no big deal. I know exactly why it's crashing. But this time when I display the stack content, it will tell me exactly which part of the file is stepping on. Okay, so we'll do the same thing, examine 8 bytes, each one in hexadecimal. And well, we can do characters too, which is actually handier because this way it actually prints the character instead of the hexadecimal representation of the ASCII code. Where the stack pointer is pointing at. So RSP is the stack pointer. And this time we see uppercase R. Okay, cool. We only have one uppercase R in the entire file. So now I know where I need to look. Okay. So by changing these 8 bytes in the password file, I can now control where it returns to. So that solves one part of the problem, which is how do I get control over this program? It's by changing these 8 bytes. That's the first question. So the second question is, now that I get the steering wheel, which way do I want to turn it? That becomes the second question. Is that okay? Making any sense? Okay? All right. So let's try to answer that particular question. So to answer that question, let's run the program again. Okay, this time without GDB, because I don't need GDB in this case. Give it some wrong password that is not too long. Press the enter key. It prints the message. That's the only clue I have, okay, of the branch. When I do not enter something correctly, it's going for the subroutine or the code to print this particular message. So my only clue is RTFM exclamation point. If I can find out exactly where in the entire memory of the program are these characters, that will give me the secondary clue of, oh, I know exactly where it used its string to print it out, and therefore I can identify the branch of when I enter the wrong password. If I can identify the branch of entering the wrong password, maybe I can find the branch of entering the right password. Is that okay? Okay. So let's go ahead and check out, this is called Hex Dump. Hex Dump is a program that you can install on Linux, Mac OS X and Unix systems. And its only job is really to do something like this. Okay, it just prints out every single byte in the executable in hexadecimal representation of the ASCII code, and then also as the ASCII code itself. Now, obviously, this went past a little bit too fast. I couldn't read everything. So I'm going to go through less this time. Less is what we call a pager. It allows you to go page up, page down, search, and so on and so forth. The joke about less is more. No, I take it back. Less is more than more. That's it. Because the equivalent command in DOS is called more, M-O-R-E. Okay? But more can only page down. It can never let you go back up again. It cannot search. A lot of functions are lacking with the program called more. The program less, on the other hand, allows you to go up, down, search for patterns, and so on and so forth. So that's why the joke is less is more than more. Okay, very geeky kind of thing, but okay, so we'll look for DMCA, okay, or DMC just by itself. Cool, we found it, okay? So we found the message itself, and we also found the other string called trusted user, okay? So maybe these locations are kind of useful to us. So what we'll do is we'll remember the offset, okay? The offset here is 670, which means in hexadecimal, these bytes are 670 bytes from the beginning of the entire file, okay? But that's the only clue I have, so I'm gonna write it down. So let me use a mouse pad here just to write it down. Okay, so we want to write down 1, 2, 3, 4, 5, 670 has the string of DM, RTFM, RTF, DMCA. There we go. Exclamation point. Okay, so this is our first clue. Okay, we got this clue about this location. Okay, so we quit from hex dump. So now I need to look into the program code itself and go like, where is this address passed to a subroutine call? Okay, in C and C++, you have cout, right? But cout with less than is translating into a function call of some kind. In other words, that address has to be pushed on the stack at some point. That would be the indicator of, oh, you're in the branch when the password does not match. Is that okay? So I'm going backwards. I'm going from what I can actually observe in the program to go backwards to try to figure out the structure of the program. Okay? So another program that is really helpful is called Obj Dump, Obj Dump. And in this one, I can do disassembly of the program. So I'm going to pipe it through less also. So you can see, it is actually showing us, okay, first of all, do these addresses look familiar? They should look pretty familiar because, the crash address looks like this, 400 and then something. It's a RETQ instruction, but this is in the right range of addresses. Okay, so we're looking at this, and we're trying to look for the pattern that we saw earlier, which is 670. So, well, we can look for 670 and see if we can find something like that. Well, we just found it. So the entire program is offset by 400, 4 followed by 5 zeros. Okay, that's the offset from the very beginning. And you can see the next thing that this does is call Q. Do you see that? Call Q is right below, and this is being passed as parameters because the call itself is put as, or put string. Put string takes one single parameter, which is the pointer to the string that you want to print. So that gives me a pretty good clue that this is the branch. This is in the branch of not having the password to match. Is that okay? Maybe, sort of? Okay. So, but before this, we got some other stuff too. So let's look for other occurrences of 670. So we have another 670 here, and those were all the occurrences. Okay, so if this is the actual, printing of this of that thing, of the message, RTF DMCA exclamation point, and then you look into this program. Okay, so we try to go backwards, and you can see the program. I mean, the code right before this line is a jump, which is equivalent to our jump I. Okay, they just call it jump, but it's equivalent to our jump I. So now the question is, hey, if the instruction right before is a jump, how can this program ever get here to give us that message? Another jump, right? So we are looking for another jump to this location, which is 5BA. Do you see a branch, possibly, most likely, a conditional branch to 4005BA in this code? Okay, so we got a JE right here, right? That is really cool, because now we can identify a conditional statement. Why do you think I know this is a conditional statement? Is there any branch that we can see here? There's a return here which marks the end of a subroutine. Okay, so none of the code should exceed this point. We don't have to analyze anything below the RETQ, because hey, after a subroutine returns, it doesn't belong to the same subroutine anymore. So before the RETQ instruction, are there any unconditional branches that goes back to the earlier part? I don't see any. Okay, but we saw the JE instruction to go to here, to go to the instruction that we want to, that we intercepted. Okay, and then we saw another one to jump all the way forward to 5C4. 5C4 is right here. What does it look like to you? The 5C4? No, 0, 0. The 00. Where?
Right, by the moon, by MOV. On the line that's 5C4, the MOV.
Oh, it's a return value. That is correct. Okay, so the convention of GCC with this processor is it does use EAX as a return value. Okay. But if you look at this code, let me highlight which part I'm talking about. So if we are only looking at this chunk of code here, what does it look like to you? We are testing something, okay, which is the same thing as our AND AA kind of instruction. We're looking at one register and use it to set all the flags, okay? And there's a JE instruction, which is equivalent to our JZI instruction, jump if equal to or jump if 0. And it is going to a future point of 5BA. And then this in return is going to fall through to a label that we also branch to, but from another branch. So what is that resembling to you in terms of a structured C code? We only got a few. We have loops, we got a while loop, we have a do while loop, and then we have if then else statements, or just an if statement. Which one do you think this resembles? No, a do while will have a branch going back. We do not have any branch going back, which means that this cannot be a loop. So is it an if or is it an if then else? Does it only have a if then? Does it only have a then branch, or does it also have an else branch? If it has an else branch, we have to branch around the else branch. If it doesn't have an else branch, then there's nothing to branch around. So the question is, do you see anything that is branching around a chunk of code? Yeah, we see that. This jump here, jumping to 5C4, is branching around whatever is in between. So this is identifying, so now we can identify this as an if, then, else statement. Okay? The else branch is printing RTF DMCA. What do you think the then branch is probably corresponding to? That we got a good password. Okay. So I got nothing to lose. So I'm going to try and say, what if I can force this code to go straight to 4005AE, which according to this code seems to be corresponding to the then branch. Is that making any sense? it's a conditional statement. Okay, it has got two paths. One path we know is going to print RTF DMCA exclamation point, which means your password is not matching. I cannot let you through the program any further. The other branch is probably corresponding to, yep, the password does match. Let's go ahead and use this program. Is that making any sense? Okay. So I'm going to write this down on my notepad here. Okay. So we'll copy and paste the address that we think is corresponding to the branch that we want to go to, and then we'll put it into our little scratch pad here. Okay, so this is the location to go to. And then the other thing we also want to kind of take a quick look at is how a call instruction is constructed. Okay, and also how the return address is going to be specified. This is relative. So the call queue instruction is relative, but when it returns, it does look at all 8 bytes or 4 bytes. Okay, I cannot tell whether it's using 4 bytes or 8 bytes, but because of the little endian nature of the processor, we can overwrite 8 bytes, and then we'll figure out which how it should be formatted. Is that okay? All right. Okay. So we got quite a few clues already, and the location we need to go back to is this particular address. So, and then we'll crash the program just one more time. Okay, we'll crash it one more time just to in GDB, just so that we can be sure what the return address should look like. So and a full address looks like this. We are looking at 64 bits, where most of it are zeros, and only the least significant portion are not zeros. So this means when I'm corrupting the stack, I kind of have to be careful, because I don't want to overwrite the more significant zeros unnecessarily. I just want to overwrite the 9B, the 05, and the 40 with what I need. Because if I overwrite these zeros to be not zeros anymore, I cannot get back to the location that I want to get back to. Is that making any sense? Okay. Okay. So that means when I do a IR, not IR, but x/8 BC $RSP, I need to write this down because it is the 8 that is important. The 8, 9, A are the important bytes because those specify the 6 digits that I need to overwrite. The other ones I probably should leave alone because they should be zeros. Okay, so I just want to overwrite these 3 bytes, the 8, 9A that is before the R. So I'm going to jot down that note again. Okay, so we'll jot down this note here, and we say overwrite 8, 9A right before the uppercase R. And we also want to know what to overwrite it to. And oh, I remember that already. We have to overwrite it to AE 05 and 40. Is that okay? So I'm going to go back to the password file now, so that I don't make it longer than it needs to be. So we go back to the password file. We locate the uppercase R because that's an indicator. We also know that we just want to overwrite 8, 9A, and then the rest we don't want to overwrite. Is that making any sense? Because we want to keep those things as zeros, as many, because the most significant zeros we want to keep. Now you can always say, oh, but we can insert additional null characters here. Yes, we can, but most of the time the null character is not going to be read because of the null termination nature of a string. So those additional zeros will not be of any effect anyway. Okay, so after we change this, then we go back and say, okay, can we crash the program again to confirm that? So we'll go ahead and check it again. Program is going to crash again, and this time it crashed at a different location because the return instruction actually did a return, but to a location that, well, look at the return location here. Don't you think that looks a little bit suspicious? Don't you think it confirmed that we have found which 3 bytes truly dictates where it's going to return to? Look at the address. Read it backwards, okay? Now, when I say read it backwards, I don't mean every single digit. I mean every 2 digits, look it backwards. 38 is the ASCII code of 8. 39 is the ASCII code of 9. And then 61 is the ASCII code of lowercase a. Okay, the rest are all zeros, which we want to keep. So now we have located the 3 bytes that we want to play with. Is that making any sense? Okay. So only one more thing to do using one more tool. Because I need to overwrite those 3 bytes to AE, 05, and 40. 40 is easy because it is a printable character. AE is not printable, 05 is not printable. So most editors cannot do this. You cannot enter those bytes into a text file. That's why we have another program called hexedit to do it. Not sure whether it's installed here. We'll give it a try. Not installed. That's okay. I'm trying to remember my root password. There we go. I think it was tech is great. Something like that.
Facts, true statements.
True statements, yes. And I know this is being recorded. Oops. Uh-oh, that's not good. Now everybody know my password. And of course, the first thing I do tonight is to check all the incoming, attempt to log in using that particular password, and then reverse, look up the IP addresses to find out, who took that bait. Okay, so now we have that program installed, which is great. So hex edit, the password file, go all the way to the end. Whoops. Okay. So you just need to move the cursor key. This is, by the way, one of the really, really cool programs because you can go to any byte location and change the location to whatever content you want to specify. So we just have to look up, how we want to change it. So the least significant byte, which is the earlier byte here, is AE. The next one is 05. And then the next one is 40. Okay. And then we save the file. I think it is Control X. Yep, there we go. Save. There we go. So now I have my password file, truly specialized to cause the program to crash, but not to crash entirely, but to crash it and return to the place that I suspect is thinking, that the program has been authenticated. So we'll hack the program again, or we'll run the program called hack. Hey, where's the program? Hack 1. Redirect the program, the file, one more time. Oh, it's still not working. Okay, let's GDB again. Okay, we are off by 1. I did not overwrite the correct ones. Okay, clerical error. So one more time, hex edit. What was it again? Test. Yep. Okay, so I was off by 1 byte. Okay, so overwrite this AE, and then 0540, and we can just put a 0 here. I'm not sure whether the tool has an option to remove a byte. Putting a 0 there is going to be okay. So we want to run the program again. And this time it says, hey, welcome back, trusted user. You got the right password. So that's the program hacked. Any questions? Well, is it legal? Well, since you can hack your own programs, exactly. So it's okay if it is your own program. I did write this program myself. So even if you forget the code of your own program, it is still your own, and it's still okay to hack it. Second question. Well, most programs are not going to be looking for a password like this. So how does a hacker attempt to hack a program? If you are a hacker, okay, put yourself into the shoes. Put your shoes into. That's like backwards. Huh? Yeah. Well, that's because of the TSA thing that we talked about early in the class. My neuron is still firing with all that patting down stuff, traumatic experience. Okay. So if you're thinking like a hacker, what are you going to do to attempt to hack a program? But how do you crash it? You're looking for assumptions, okay? So the first thing is you're looking for assumptions that are common amongst, careless programmers, okay? What kind of assumptions? Where do you start when you're looking for assumptions? Common mistakes. User inputs. Okay, we're getting warm. Okay, inputs of some kind. Okay, but it doesn't have to be user input, because programs that are interactive with end users, they're not usually very infrastructural. In other words, they're of value maybe, but they are not server programs. You can crash Twitter. You can probably do it, but with Twitter, what I would do is to have a different program to inject, strings or inject content onto a stream to go to the Twitter, server. But what kind of assumptions are we talking about? Okay, assumptions have to do with standards. Every time there's a standard, there will be assumptions. Okay, so we can look up, some standards here, and we can look up something that has been used already. So GIF file, okay. Format, okay, and once you look it up, you can see how, okay, let me just locate the correct portion here. File format, there we go. So every time you have a file format, okay, so is there a better way to display the file format? Okay, there's a trailer. Okay, so let's find out the trailer. There's only one occurrence, so that's not going to be helping me. Okay, let's look for a JPEG then. But every time you use a standard, there are assumptions. Okay, so let's look up JPEG, file format, syntax and structure. There we go. All right. So every time you look into something like this, and typically you can find these in RFCs. Those are basically the files in industry to define standards, especially for protocols like HTTP and so on and so forth. So over here we can see that there are byte offsets, and it says what it does. But what we are looking for are things that are variable and things that are null terminated. Because things that are both null terminated and also has a maximum size is where most of the problems occur. Why do you think that is the case? Let me say that one more time. Standards that has to do with a field that is null terminated, expected to be null terminated, but at the same time it also has a maximum size, is where we can start the hacking attempt. Why do you think that is the case? You have what kind of boundary conditions are we talking about? What do you think a careless programmer is going to do when the programmer reads the standard and it says this string is going to be null terminated?
He's not going to look for a null. He's going to assume it's there.
Exactly. The assumption. So remember assumptions? So the assumption of the programmer reading a standard is the file conforms to the standard, which means the string is not only null terminated, but also conforming to the size limitation. Is that okay? So if for whatever reason the string has to be copied locally to do some processing, the buffer is going to be the same size as what the standard calls for. Okay? So if the standard says, okay, this string, which is the comment of this particular file, can be up to 4 kilobytes, and it's null terminated, the programmer will just allocate a 4 kilobyte local buffer to copy the string from the file to the local buffer, and assuming it is terminated correctly and has the right size. Is that making any sense? Okay, so that means in coding, the programmer who is not careful is going to say, oh, okay, I'm going to define a local variable char. Okay, so let's call this, process comment, and you're passing some kind of structure, blah 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 here. Okay, that part is not important. The important part here is, in order to process the comment, the programmer, the careless programmer, is going to say, okay, I'm going to declare a buffer of 4096 bytes here, because that is the standard. The standard says the comment should not exceed 4 kilobytes. That's the first assumption. The second assumption, which is the fatal one, is to use string copy instead of string and copy. So it's going to use string copy to copy the buffer from whatever the structure is pointing to. So, okay, or whatever the string pointer is pointing to. So let's call this const char ptr here. This is the fatal mistake, because it is assuming that the string that is incoming from a file is null terminated, but it is also less than or equal to 4096 bytes. So a hacker will first look into something like this. It is both null terminated, or there's a terminating character to say this is the end, but also at the same time there's a size limitation. The size limitation is what is causing the programmer to allocate a buffer of a certain size. The null termination part is basically telling the programmer and go like, oh, you can just use string copy. And the combination of these two, the size limitation, which is assumed, and the null termination, which is also assumed, is what allows a hacker to now specify in a file, okay, with a comment that is actually null terminated, but is more than 4096 bytes. The excess of that string, which is coming from a file, is going to overwrite past the end of what is allocated here into the rest of the stack, which is what we observed a little bit earlier, which enabled the kind of hack that I just did, because it is overwriting a portion of the stack which includes return addresses and other things. So by carefully controlling what you're overwriting and how you overwrite it, you might be able to gain control of the program. Now, this program is executed on a platform that has the execution inhibit bit already enabled. Let me look it up for you so that you know what we are talking about here. Because there are multiple types of Stack Overflow exploits, and the execution inhibit bit. Okay, that should be close enough. NX bit. Okay. So the NX bit, which is no execute bit, is a technology used in CPU to segregate area of memory for use by either storage of processor instruction, or for storage of data. So the stack is going to be classified as, guess what? Storage of data. You cannot execute code that is on the stack. That was the earlier hacking code actually would put executable code on the stack and then return to that code. So you have more control over what kind of code to execute. Modern processors already have the NX bit to get rid of those particular problems. But what the NX bit cannot do is altering the return address to a different point of the actually legitimate program that you're running. So by controlling where you return it to, you can still gain a certain degree of control to make it do things that it is not supposed to, which is what I just did with the program that I demonstrated. Is that okay so far? This won't be in the final exam. I'm not going to give you a program like this and say, okay, no. Better yet, the program is what I use to enter your grade. Give me a file that can enter your own grade, and that will be your actual final grade. That was actually one of the security classes at a four-year university. I think that was how the final assignment was graded. Was hack the server to enter your own grade. Well, I mean, it's appropriate for certain classes, but not in this class. But do you guys, some of you probably, can link what I did, the concepts involved, to things that we have learned in this class. Okay, now we did not talk about the x86 instruction set, so that instruction is completely foreign to us. But you can also see how the mnemonics are very similar. Okay, we have JMPI, it has JMP. We don't have a return instruction, it has a return instruction. We have JZI, it has JE. We have JMPI, it has got JMP. And there are many kind of related instructions. So the more you're exposed to different architectures, the more you will be able to identify those mnemonics, even if it is your first time reading the mnemonics, because there are only so many variations of those things. Okay. The second thing has to do with the use of GDB. Now, the GDB can be used on the Intel architecture, which I just did. But if you have a Raspberry Pi which runs the ARM architecture, guess what? GDB is available too. And the ARM mnemonics are very similar to the ones that we use in the toy processor. So there's load, there's store, okay? Jump is usual, there's call, there's return. So you will be able to recognize some of those instructions as well. If you cannot recognize, just look it up. I mean, the mnemonics are published, okay? What is also common across almost all platforms is how the stack is used. Almost in every single platform, the stack start at a high location when it's empty, or the stack pointer, I should say, start at a high location when it's empty. And as you start to push things, the stack pointer goes lower and lower. That is almost a universal standard. It's also almost a universal standard that the return address is on the stack. Another universal standard that your local variables are also on the stack. So the program that I just did, if I were to rewrite the same program or recompile, I should say recompile the program in other architectures, I can use the same hacking technique to accomplish exactly the same thing. So it had nothing to do with the architecture itself. It had to do with how programs are compiled and how memory is used on the stack for local variables, parameters, return addresses, and so on. Is that okay? So why am I teaching you guys how to hack? Now, I understand this is completely made up. It's not a real scenario, because a real scenario would not be illegal, for one thing. So why do you think I'm teaching you guys how to hack?
So we can stop hacking.
That's one thing. Well, the primary purpose is to kind of relate what we have learned in this class to something that actually can be done, okay? And then the second one is to enable you guys to pick up jobs, or at least, start to have some interest, hopefully, to pick up jobs in other classes that will actually teach you more about computer security. And when I talk about computer security, it is not, oh, turn this switch, switch that knob, slide this slider to make your computer more secure. We are talking about actually writing code that is more secure to begin with. Starting with, do not use string and copy. I'm not kidding. It is actually on the man page. Okay, if you say man string copy, it is on the man page right here. Beware of buffer overruns. Even the man page says it is not a good idea to use string copy. So let's just say that this man page was last updated in 2012 to include this little statement here in boldface, okay? How much code do you think is written before 2012 that is still in circulation?
All of it.
A lot, okay? Now, a lot of code, a lot of program has been, a lot of debugging and fixing has been done since 2012, but a lot of programs still has a majority of the code base that is done before 2012. So that means we are still suspecting that a lot of programs are still using string copy instead of string and copy, and similar other flaws that people are using. Okay, let me show you another one that has a great warning too. Get string. Read the warning. The first thing in description. And why? Why do you think that is the case? Let's find out what the program is supposed to do. GetS reads a line from standard input file, which is the same thing as your cin in C++, into the buffer pointed to by the pointer s until either a terminating new line or EOF in a file is encountered, which it replaces with a null byte. Okay? It only has one single parameter. So that means we cannot tell GetS how long that buffer really is. How many bytes have we allocated to store this string? GetS doesn't know. It's not being passed. So it doesn't know where to stop until, so it's not going to stop. So the bottom line is it is not going to stop until it reads a terminating new line or end of file. So the flaw that we saw earlier can be repeated here. So string copy, GetS are the two bigger, basically, flaws that we have seen. Yep.
Why haven't they just taken it out of the standard library and like put it in a separate library? I mean, why it was really never used this function? Why should it be in the standard library?
Maybe educate people. Why you don't want to use this function?
Okay. Now, even if you were to take out this function completely out of the library, people can still write their own subroutines making the same mistakes. Assuming things are null terminated and enough space is already allocated. That is the basic flaw. You cannot stop everything just by removing the library entries, because people can write their own subroutines, or maybe even not subroutines. They just have a loop and say, while star PTR does not equal to null, continue to copy to the next byte. You cannot stop that one easily, because now you actually have to analyze the code, recognize this is a loop. It involves checking for null. There's an increment of a pointer, and then there's a store somewhere in the loop too. That becomes a lot more difficult than just recognizing, oh, this is a call to GetS. Let's stop that. So it's a fundamental concept to analyze a program that the programmers are trying to make. It's an assumption issue. Okay, people are assuming the incoming streams of bytes are playing by the rules, and that's exactly what hackers will try to do first. Is to say any place there's a rule, any place there's a standard that says we're expecting this, they will try to break that. So what do you think is the outlook of these jobs? The anti-hacking kind of jobs. How does that compare to game development? Because at the Design Hub we have a whole bunch of guys who are saying, oh, we want to go game development. So how do those two compare? Game developer on one side and computer security expert on the other side that can do something that along the line of what I just demonstrated.
Keep people from cheating.
In game development, right? Okay, but what I'm looking at are two things. Okay, what I'm looking at are two things. One is job security, and one is pay scale. Okay, how would you compare these two?
Security's going to pay more.
Why do you think the security people are paid more?
Security can keep entire corporations safe, while game development can keep a couple thousand players happy.
Would you worry if you're a game developer? Okay, let's say you're the manager of a game development company, and one of your engineers or game developers decides, I'm not going to work for Riot anymore. I'm going to go work for Steam, okay, or whatever, okay. And every single week, every single month, you have like thousands of incoming resumes, saying, oh, I need a job. Are you guys hiring? So what are you going to say to this engineer or developers saying, I'm quitting this job? You give that person an empty box, right? Use this, okay? We got plenty of boxes here. Okay, so on the flip side, you're working for, let's say, Wells Fargo Bank, and you're an expert in computer security. You can do stuff that I just did, along with your SQL injection test and all kinds of stuff, okay? And you're going like, I'm quitting this job and I'm moving out of the country. What do you think your manager is gonna be? Your manager is gonna respond to that?
Here's $400,000 bonus. Yeah,
This is more money. Don't leave.
please.
Well, I cannot say that the part that I really want to say, which is funny, but your boss will be very concerned, okay? Especially the part that you're moving out of the country, okay? Because if you say I'm moving on to Bank of America, your boss will go like, okay, you know,
'Cause
but
you're gonna end up knowing all these secrets, so you're gonna know how to break everything that you.
but you won't do it on U.S. soil because you know you can be caught and be brought into court. But if you're out of the country, you can do it. You can do it somewhere in Bangkok, okay? In a cafe, in a coffee shop,
Go join a hacker collective in Russia.
or the anonymous, okay?
Didn't someone do that to like Facebook?
They're pushovers
Huh?
now.
I believe there was someone that did that back in like 2000.
Yeah, they gotta
Yeah,
fix
but
that.
but the whole point is, the point is, if you get into the computer security field, especially at a level where you are the one who can find out, new techniques of hacking into programs so they can secure programs so that they cannot be discovered by somebody else. If you can work at that level, I think your pay is going to be fairly good. And two, you have job security because companies cannot afford to lose you. Game developers are a dime a dozen, okay? And if you ask low-level game developers, doesn't matter which company, it's a sweatshop. It's basically a sweatshop. They just keep working people, and the programming that you're going to do is not really quite that exciting either. Because when you're programming a game, what do you think the majority of labor goes into game development?
Playing video games all day long.
No. Seriously, okay. Some people have worked in the design hub, not in this class, unfortunately. But there are some students who work in the design hub and they're developing a game called Snow Wars. Okay. So the question is most of the work actually exciting coding and figuring out the software architecture and stuff like that, or is it mostly I need to do the animation of this snowman, so when it moves through snow, it looks right and not just skidding and doing a moonwalk on snow. Most of it is just that, and debugging, the visual effect, getting the menu to look right, getting your game to appear right on screens of different resolutions, tedious stuff like that. The game engine is already done. Unity is already done. You're not programming the core of Unity itself. You're only making Unity to make things look right on the screen. Now, there's a certain part of coding, like, when this snowman crosses here, we're going to shoot a flamethrower, okay? Okay, there are some triggers, that you can program in. There's some visual effect that can be very cool. But for the most part, I wouldn't call it very exciting. It's a good resume item, by the way, but that should not be your ultimate objective. I think you can shoot higher. Is that making any sense? Okay. All right. So I hope you find this particular lecture, kind of helpful, at least in the sense that it's connecting concepts that we have learned in this semester to something that is actually practical. This is not a toy processor. The i5 processor is not a toy processor. At least I hope it's not. And the technique that we practice on the toy processor is transferable to actual real processors. Is that good? All right, so we are moving on to the lab. There's a new lab activity tonight that is due in a week, which means it is before lecture next Monday. So you got tonight's lab and Wednesday's lab to do it. But you can also do it over the weekend if you want to. It's just that it has to be turned in by 7 p.m. next Monday.
Are there setup questions like the other one?
Huh?
Are there lead-up questions like the last one?
Yeah, there are like a few really low point values.